Doug Littrell again. It's June 12th. This is video number 12. Yesterday, in my first take of video number 11, I was able to mention these two pages about time dilation. This is about the GPS system, and this is also about time dilation, embedding time dilation. So it's in the book. Going to double check something with that today. So I want to start off by reading. Before I do that, I want to mention in relation to the Earth spinning, what I was talking about yesterday. We were talking about, okay, the spinning, or what I was talking about, the spinning of the Earth has its own momentum, and it's sort of like a gyroscope, and the momentum that a person would enter into when spinning, well, it's like a car when you're traveling down the highway. You don't feel, you might be going 60, 70 miles an hour. You don't feel, it feels like you're sitting still because you and the car have the same momentum. And so that's the way it works with the Earth spinning at roughly 1,000 miles per hour. You don't feel it as far as G-force. But, however, the spinning does have an effect on the force of that you're being pulled down by gravity to the Earth. There is a centrifugal effect caused by that spinning. The Earth, of course, the technical term for its geometric shape is a oblate ellipsoid. The first person, I think, that realized it wasn't perfectly spherical was Isaac Newton. Said he believed it was a oblate spheroid, but we call it an ellipsoid now. Anyway, that's all good stuff. But the point is, I heard a person make a point about this a couple of years ago in a video, I believe it was, and very valid. I believe it's been checked well. Makes all kinds of sense, not counterintuitive. When you're standing on the equator, you're traveling, roughly 1,000 miles per hour. If you're say some halfway between there and north or south of the equator and the pole, then you're moving at a less speed as the Earth spins. If you're standing exactly on the pole, North Pole or South Pole of the Earth, you're doing a pirouette instead of traveling. You're standing in place, but you would turn in a 24-hour day and make a complete revolution. This does affect a force. This spinning at the equator and at different latitudes north or south of the equator until you get to the North Pole. Well, even at the North Pole, you still have, or South Pole, you still have, if you stood on a scale that tells you your weight, you would weigh less at either pole or near the pole than you would, pardon me, it's the opposite of that. You would weigh more than you would at the equator, because at the equator you're experiencing something that the Earth is experiencing, that there's a centrifugal force that's trying to throw you out, the motion and the turning. The desire is, in motion, is for your body to continue in a straight line. That, because you're held to the surface by gravity, that results in you weighing less. And now it's not very much. So this isn't a big player, but it is true that you weigh less at the equator than you do at or near the North or South Pole. So, we want to get things as accurate as we can when we're talking about these things. I thought I needed to include that note. Now, there may be something else about that I need to mention, but let me go ahead and revert back to this time dilation and GPS satellite uh, uh, issue or item. Um, I want to read from this page a little bit because I'm going to do a math function and I'm going to tell you the result. We're going to double check this, approach it in a different way with through math. So I'm going to read the first sentence here. It says, and a few more. Radio waves traveling at the speed of light cross 299,792.458 kilometers per second, which is 299,792,458 meters per second. That translates into 186,282.397 miles per second. There are 86,400 seconds in a 24-hour day. Thus, 186,282.397 miles times 86,400 seconds equals 16,094,799,100.8. That is over 16 billion miles of radio travel per day. That's how far an individual radio wave would travel, or a wave of light would travel in a day, visible light, let's say. Okay, converting that miles per day value to feet per day is 84,980,539,252,224. That is okay, that's feet per day, which is over 1 quadrillion inches per day. Okay, that's 1 quadrillion, 19,766,471,000,000 and 26,688 inches per day. Okay. Anyway, for this, I've been working on a scientific calculator. I learned how to do that in 2015. Did a lot of calculations back then. Still do some from time to time. I think the one I use is supplied by Google. Seems to work pretty well. Appreciate it. But anyway, to solve this problem, about how much radio travel is in for the adjustment for relativity per tenth of a second GPS transmission, satellite to ground or ground to satellite, how much that is actually affecting the accuracy of the system. That adjustment for GPS for relativity that's made over a 24-hour period of 38,000 nanoseconds. One of the things you need to do first is find out how many inches of radio travel is in a nanosecond. That's one of the things I did first. Then you need to find how much that adjustment for relativity per 24-hour day is being applied within a tenth of a second GPS transmission. And so when you do the two and then you combine those, then you solve the problem of how much it's really affecting the accuracy of the GPS system. One of those numbers I came up with was that the distance that radio travels in a nanosecond is about a foot. It's 11.80 inches. So I'll come back to that number before this is finished. Okay, we come up with 1583.333 nanoseconds per hour. Okay, in this adjustment for relativity. Now we know how much per hour. If it's 38,000 per day, now it's 1583 per hour. Now we divide that by 60, and it is 26.3888 nanoseconds per minute. Now we divide that by 60, and we got this adjustment for relativity is see if I've done this correctly here. Okay, I divided it by 24 and came up with 1583. Then I divided it by 60. And I came up with 26. And that's so 26 inches, or excuse me, nanoseconds would be for the relativity adjustment for the GPS system per minute. And then you divide that by 60, and I come up with 0.4398 nanoseconds per second. That's 38,000 nanoseconds per 24-hour period, now broke down into how many of those is being adjusted per second. And it's less than a complete nanosecond. It's less than half of a nanosecond per second. Now you divide that by 10, because we're talking 1/10 of a second transmissions. And you come up with 0.04398 nanoseconds per per 1/10 of a second GPS transmission. So now you take that times the figure we found for this 11. Well, it's about 12 inches. That number back up there. That 0.04398 number back up there. And now we're going to take it times a foot. How much radio travels in a nanosecond. Because this is how much the adjustment, how many nanoseconds the adjustment allows per 1/10 of a second GPS transmission, which is 0.04398 nanoseconds per 1/10 of a second. So we're going to take the amount that distance that radio travels in a nanosecond. It is basically 11.80, almost a foot. And we come up, and there you have it. Looks like my double checking verifies what I have in the book. And you come up with a 1/2 inch. It's 0.51898 inches. That's a 1/2 inch. A 1/2 inch of radio travel those 38,000 nanoseconds sound like a lot, but when you break it down into a tenth of a second GPS transmission, anyway, a half an inch doesn't have anything to do with GPS accuracy. The tolerances are greater than a half an inch. Yeah. So there you have it. Looks like my book is good to go on that issue, on that item. And so for my conclusion to video number 12, which I was lying in bed thinking about, something I wanted to say, I would compare relativity to religion. Religion says it gives you lots of things, but it really doesn't give you anything. I mean, yeah, it's going to give you some friends that are into that, and so you associate with them, you get support from them, and etc. But as far as actually giving you life after death or anything of real substance, other than some friends who are also deceived by it and manic because they think that they've got all these promises they've obtained by faith. Anyway, like religion, relativity also doesn't really give you anything. It's just like that half inch, supposedly, that it's correcting for the GPS system. It's just, it's really doing nothing. Okay? So to me, it's just like religion. It's a bunch of baloney. Sounds like a big deal. Everybody thinks it's so cool. But it's nothing. It doesn't give you anything. It's like religion.